Hi, I'm Sam and welcome back on our journey through basic graph theory. Just a quick point to note, so although the presentation is dated 8th of March this year, that's when all the information is correct to. The presentations will be published further and further from that date as we go forward. In the last presentation we covered part 1.1, what a graph is and what it's not. In this presentation we'll cover part 1.2, graph components. There's no change to the aim of this series presented in part 1.1. The main goal is to be able to understand graph theory concepts to enable analysis of networks in general. In part 1.1 I provided a general vicinity in which graph theory resides. It's not lost on me that it wasn't exactly a short story using the 100 most common words in the English language, and that there was some degree of assumed knowledge. Throughout this presentation we'll home in on some key terms and concepts which are a bit more specific than what we covered in the last presentation. The use of the grey term tiles will become more noticeable as we start to cover more and more standardized terms. If I could summarize this presentation in 2 words, I'd use bracket fiesta. Although we've avoided a large volume of Greek symbols, the number of brackets required to explain the elements of sets, multisets and ordered pairs may seem a bit over the top at a glance. We'll essentially walk through the courtyard of graph theory, and at any point you get lost or discrete mathematics textbooks aren't your Netflix and chill, then I'd encourage you to be curious rather than cautious. There's many great resources on the internet that can help you out as we go forward. Sal Khan actually has a great TED talk on teaching for mastery, and my advice would be to set your concrete before you build your house any further. If the random combinatorics and set theory references don't make any sense to you, then please do be curious rather than cautious and take advantage of the wealth of resources that are online. Just on another point, I'd assume that, just take this example, you wouldn't think you were stupid because you didn't recognize a random Japanese kanji. You just need a dictionary. So if you approach maths as a language, it may alter your perspective on the subject because at times just plain English words don't mean a lot more than a string of set builder notation. IDGARA, to steal a phrase from the late Robin Williams. This string of letters means absolutely nothing to anyone unless you've watched Patch Adams. In the same vein, a random existential quantifier and handful of what appear to be wingdings won't mean much unless your audience know what you mean. I hadn't touched maths since university 15 years ago, and I literally had to start at year 10 and work my way back to second year tertiary study. So the Khan Academy and other YouTubers provide great resources which are all free of charge, and most texts are available online as ebooks, either free or at relatively low cost. Okay, so enough of the world according to Sam, let's get into it. References. There's no change to the short story of references that I've presented here in part 1.1. I've just presented them here again, given all the material is drawn from the consulted text, which some pretty sweet PowerPoint animation skills have enhanced a little bit. Part 1, Basics. Part 1.2 is nested under the umbrella of Part 1, Basics. What makes a graph? Diestel 2017 states that much of graph theoretic terminology is so intuitive that it's easy to remember. Although it may be intuitive, terminology is not widely standardized across the consulted text. A good example of variation in concepts where the concepts are different but they are still correct can be seen in diets. We've seen the combinatorial complexity of diets explode in the 21st century. Everything from carnivore, meat-only diets to paleo, whole foods, vegan, vegetarian, situational vegans, supplement diets, etc. If relationships between people and foods were sets, then the diets would be functions and relations. 3 examples of varying nomenclature are given below in example 1.2a that show the variety of graph labeling across 3 different graph theory texts. The standard nomenclature used in this presentation is shown in the Balakrishnan and Ranganathan 2012 example, but a range of other texts use this nomenclature as well, such as EP 2011 for example. Note that although some texts don't use this nomenclature, I highly doubt that the authors are ignorant to it. In some circumstances, the A, B, C, D and E approach is easier to digest than the protein-rich alphabet soup of universal labeling that's presented here, in which every vertex and edge in a graph is labeled. G for graph. A graph title is represented by an uppercase G with subscript notation used to differentiate between various graphs, or alternatively different letters can be used without subscript notation. The key is differentiation. The letter G is used throughout this presentation for ease of reference as a graph title with subscript notation used to differentiate between graphs. An example of this is shown in example 12b. Note, the graphs presented here are also unlabeled. The vertices are identical without labeling or other differentiable features. The position of the vertices in two-dimensional space is arbitrary, and the length of edges connecting the vertices is also arbitrary. This makes it difficult to understand the connections between different elements, and if left untreated, provides an incomplete picture of the network represented by a graph. That said, it does reduce the potential number of subgraphs, but we'll cover this in another presentation. This brings us to our first term defined in this presentation, which is the title of a graph, shown in the grey term tile. Elements and connections. I know there were instances where I mentioned vertices and edges in part 1.1, but these terms are defined further here. The nomenclature for elements and connections are shown below in example 12c. The connections between elements can be anything ranging from handshakes to bridges connecting land masses. These are the two dominant characteristics of a graph. They are what you see. Just like when you look at a cake, you see a cake and not its recipe. Elements that we covered in the previous presentation are represented by points called vertices. Connections are represented by line segments called edges that connect two vertices. Koenig states that the points, vertices, are arbitrary distinguishable elements, and an edge is nothing other than a collection of its two endpoints. The blue box to the right of the slide shows two pairs of connected vertices with different labeling. The vertices V1 and V2 are connected by the edge E1. The other side of the same coin of a label for edges such as E1 is to define an edge by its endpoints. This is shown below E1 with the two-element set of vertices V1 and V2. Their equivalence is shown to the right. If you remember back to the example of Euler's 1736 article regarding the 7 bridges of Königsberg, which I presented in part 1.1, he labelled the graph with letters and represented the bridges connecting two land masses as a two-letter sequence. The terms vertices and edges are highlighted in the grey term tiles to the right of the slide. Vertex and edge sets. The collection of vertices and edges are defined by their sets. If vertices and edges were marbles, their sets would be the bags they belong in. In a graph, the vertex set V of the graph G is denoted by Vg and contains all vertices in a graph. Similarly, the edge set E of the graph G is denoted by Eg and contains all edges. These sets are shown below in figure 14. The sets V and E are disjoint. The intersection of set V and E is the empty set. That is, they don't intersect. This is shown below in figure 14. An element of the vertex set, Vi, where I could be any number of the given vertices, is an element of Vg if and only if I is an integer and I is greater than or equal to 0. And this is given by set builder notation, where the set V is a set containing the elements Vi such that I is an element of the integers and I is greater than or equal to 0. The same can be said of the edge set. You can have a graph which has no vertices and no edges. This is the same principle as having 0 in the Arabic number system we use today. It has limited utility in some areas, but its inclusion allows us to rationalize a range of concepts. The vertex and edge sets can be empty, finite, or infinite sets. Since the vertices and edges are the building blocks of graphs, a graph is said to be a tuple. G is equal to VE, the ordered pair of the vertex and edge sets. This is given by Raman 2017 or by Diestel 2017 as a pair consisting of the vertex and edge sets. We'll cover the building blocks of graphs throughout this presentation to give you an idea of the varying components that different texts include or exclude to define them. Example 12D shows the vertex and edge sets for a simple complete graph G1. G1 has 3 vertices and 3 edges annotated in their respective sets. On this slide, we've covered 2 important terms, the vertex set and the edge set, shown in the grey term tiles to the right of the slide. Vertex and edge sets. Power set. The power set of set A is given by PA and is the set of all subsets of A. Note that the power set of A includes the null or empty set and the set A itself along with the other subsets. The power set of both the vertex set and the edge set are no different. I've made note of this here because it helps demonstrate my rationale for defining a null or empty graph, which is covered later in this presentation. Cardinality. The cardinality of the vertex set is given by the absolute value bars enclosing the set, and this tells us how many vertices are in a graph. DSTL 2017 states that the number of vertices of a graph G is its order, written as G with bars. The cardinality of the edge set tells us how many edges are in a graph. In the same vein, DSTL 2017 states its, i.e. the graph's, number of edges is denoted by G double bar, which is described as its size by Balakrishnan and Ranganathan 2012. This is underpinned and best introduced by Harris et al. 2008, who state the order of a graph G is the cardinality of its vertex set, and the size of a graph is the cardinality of its edge set. These are important features when understanding the composition of subgraphs. Example 12e shows a simple graph G1 which has 3 vertices and 3 edges. The vertex and edge sets for G1 are shown below in the graph. The cardinality of the vertex and edge sets, which represents the order and size of this graph, is also shown in example 12e. The power set of the vertex and edge sets are also shown below in example 12e. Figure 15 shows Pascal's triangle, the array of binomial coefficients, to demonstrate its value in identifying power set cardinality and the number of 2-element subsets. The sum of the rows of the triangle is given by 2 to the power of n to the left of the figure 15, and this is the number of subsets in a power set with n elements. I've highlighted the row with 2 elements where n equals 2 in the red box to show that it has 4 subsets, but only one of those 4 contains a 2-element subset. As we zoom back out on Pascal's triangle, the 2-element sets are highlighted in red. Note that the formula for finding the nth term of the sequence of 2-element subsets, highlighted in red, is another way of finding the number of 2-element subsets of a set if we were only given an input of the number of elements. Therefore, we can find the number of 2-element endpoint sets of a vertex set with the formula shown below figure 15. Again, we see the triangle number formula. In this slide, we've covered the power set of the vertex and edge sets along with set cardinality, which tells us the order and size of the graph. Further to power set properties, we also identified the way in which to calculate the number of 2-element subsets of the vertex set, which is important in identifying the endpoint set for certain types of graphs, but notably not all in general. We'll cover endpoints in detail in the final presentation in this series. In this slide, we've introduced the terms order and size, shown to the right by the grey term tiles. The endpoint set. The possible endpoints within a graph will always be a 2-element set, since an edge is essentially a bridge that connects 2 banks, its endpoints. The nature of the endpoint set varies depending on the source text. However, for the general definition of endpoints, we need to be able to include repetition of single vertices in an unordered manner to account for the self-referential edges called loops, which we covered in the last presentation. This is facilitated using multisets, where a multiset is just like a set, an unordered collection of elements, however, the key difference being that elements can be repeated. This is the key difference between a set and a multiset. Given that you can calculate the number of combinations with repetition of elements using the n multi-choose k equation, it logically follows that these sets would be applicable to graph endpoint sets for undirected graphs, which are the undirected line segments opposed to those with arrows, which are directed graphs. Figure 16 shows the disjoint vertex and endpoint sets. This is the second time I've referenced the endpoint set S as shown above, the first time being during the rule of association / incidence function explanation in part 1.1. I know there is some variation in multi-set presentation. Some texts use the curly braces, others use the less than, greater than arrows, but I've just used square brackets to differentiate between multi-sets, ordered pairs, and general curly braces for sets in other presentations. A key point to note is that the endpoint set is not a subset of the vertex set. Given that any subset of a given set A, for example, exists as an element of the power set of A, and so the endpoint multiset is not a subset of the vertex set. We'll explore in detail the multiset and its relationship to the vertex set in the next presentation. Moving on, example 12F just reiterates the types of edges that we've introduced so far. I've used the bidirectional arrows to show undirected edges because an undirected edge is essentially a two-way road. You can move from one end to another, and it doesn't matter on which end you start because you can travel in both directions, and that's permitted. Example 12F also shows the important fact that the two-element multiset for the endpoints of edge E1 is not the same as a multiset with a single element. This is the key differentiator between sets and multisets. Example 12G shows an example of the endpoint set for a graph G1. You'll notice that the small triangle-like graph seems to appear a lot during these presentations. Like all things, combinatorial complexity, to steal a term from Sturman 2000, increases exponentially with the number of elements in a set. So our 3-vertex friend here is great to work with to introduce concepts without blowing things out of proportion. The graph has 3 vertices and 3 edges, where each edge maps an element EI from the edge set to a 2-element endpoint multiset. In this example, you can see that edge E1 connects the vertices V1 and V2, which is the first term in the endpoint set S below. The endpoint set term is shown to the right in the grey term tile. If you're seeing out your COVID-19 isolation by consuming the monstrous daily limit of alcohol which is available in Australia, I'd advise against drinking every time I say the word set, because you're most likely going to have something more pressing to worry about than the coronavirus if you do. That said, it'll probably quench this dry presentation and make it a lot more bearable if you really don't Netflix and chill with maths. Walks, trails and paths. To effectively explain the defining characteristics of the trivial and null graphs, we'll first need to briefly introduce the concepts of walks, trails and paths. If a graph was literally a series of bridges connecting landmasses such as the Königsberg problem, then walks, trails and paths are the different ways you could structure a journey. Balakrishnan and Ranganathan state that a walk in a graph G is an alternating sequence of vertices and edges beginning and ending with vertices. So if we labelled the start and end vertices with some arbitrary values, then we could say that a journey starts at VO for origin and ends at VP. For one letter after O, not for the same reasons that we labelled the start. If we did, we would have VF for finish or VT for terminal. So back into the protein-rich paragraph above, a walk is an alternating sequence of vertices and edges beginning and ending with the vertices, in which VI-1 and VI are the ends of EI. In some texts you will commonly see AIJ or VIJ. This is the same as saying VI-1 and VI are the ends of the edge, or if we replace the I-1 with a J, we could say that VI and VJ are the ends of VIJ. This being an edge that connects vertices VI and VJ. I personally like the I and J terminology because it corresponds to unit vector terminology, and as we'll see in future presentations, matrices have a lot of applicability in graph theory. As we saw covered above, VO is the origin and VP is the terminus of the walk. Why? Well, because P comes after O in the alphabet, not because it has any real meaning. Back to the paragraph. The walk W is said to join VO and VP, the start and end points. It is also referred to as a VO to VP walk. If the graph is simple, i.e. it has no loops or parallel edges, a walk is determined by the sequence of its vertices. And this is pretty self-explanatory. The walk is closed if the start point and the finish point are equal. That is, you start on the finish point, and it's open otherwise, which means you wouldn't start on the finish point for an open graph, but you would for a closed graph. Just imagine walking around a simple route mapped out by the graph G1 shown in figure 17, or the diamond-shaped graph to the right. Then you can see that if you travel across each edge once, then you'll always finish where you start. You could just travel across one bridge, and then this would be called open because you didn't finish where you started, and thus your start point does not equal your finish point. That is, VO does not equal VP. A walk may also involve travelling a route which looks like the star or plus sign shaped graph to the right of the slide. In this journey, we would need to repeat the central vertex VI multiple times to get to VP from VO. If we wanted to cross each bridge at least once in this graph, then we would end up with VI appearing in the journey sequence at least 3 times. A walk is called a trail if all the edges appearing in the walk are distinct. That is, they don't repeat. So you cover each edge once and only once, thus the Königsberg problem rules. An example of a trail is the diamond-shaped graph in the right of the slide where VO equals VP. If we crossed each edge once and only once, moving either clockwise or anti-clockwise, then we would cover each edge once and only once. Moving on, i.e. a walk, is called a path if all the vertices are distinct. Thus, a path in G is automatically a trail in G. This means, so if you don't repeat vertices, then you can't finish where you start. Therefore, a subordinate part of a larger journey could be called a path in an overall trail, which may be part of an overall closed walk. If, however, your complete journey does not start where you finish, then this could look a lot like the zigzag graph to the bottom right of the slide. I've also shown this hierarchy of nested terms in the concentric circle set diagram to the right of figure 17, where a path is a subset of a trail, and a trail is a subset of a walk. Walks, trails, and paths continued. Following on from the definition of walks, trails, and paths in the previous slide, a simple animation is shown below in example 12H to demonstrate the difference between walks, trails, and paths. Mixer X will help highlight the paths, and the terms walk, trail, and path are shown to the right in the grey term tiles and will be covered in detail in subsequent presentations. One is the loneliest number. Okay, so moving on from some sweet elevator music to pass the time in our animation, and moving on from the foundation of walks, trails, and paths, we'll now cover the trivial and null graphs. In the endpoint set definitions previously, it's apparent that a graph can consist of a single vertex or nothing at all. I know in part 1.1 I said that a graph of nothing is of no use to no one. However, that's not 100% accurate, and in some instances it actually is of value and helps us with clarifying subgraphs or other features of graphs. Balakrishnan and Ranganathan 2012 state that a graph is trivial if its vertex set is a singleton and it contains no edges. A walk length of 0 consists of just a single vertex, a trivial graph. The length of a walk is the number of edges in it. So our commonly presented triangle has 3 edges, and a journey along a closed walk starting and finishing at the same point will have a walk length of 3. Diestel 2017 talks about the null and trivial graphs and states that for the empty graph we simply write the empty set. A graph of order 0 or 1 is called trivial. Sometimes, example to start an induction, trivial graphs can be useful. At other times they form silly counterexamples and become a nuisance. To avoid cluttering the text with non-triviality conditions, we shall mostly treat the trivial graphs and particularly the empty graph with generous disregard. A fine example of an academic burn. Figure 18 shows a trivial graph G1 which has one vertex and no edges. The vertex set is a singleton and the edge set is empty, containing no elements. The trivial graph term is shown to the right of the slide in the grey term tile. None is less so. If 1 is the loneliest number, then none is less so. Koenig 1936 states, the null empty graph, which has no vertices and no edges at all, just as the number 0 is introduced in number theory and the null empty set in set theory. Somewhat contradictory to this, we have the statement from Oyston Orr 1964 who states that the graph will consist only of isolated vertices, that is, vertices at which there are no edges. We call a graph of this kind a null graph. In his figure 1.3, we've drawn such graphs for 1, 2, 3, 4, and 5 teams or vertices. These null graphs are commonly denoted by the symbols n1, n2, n3, and so on, so that in general nn is the null graph with n vertices and no edges. I think that this approach has some value given that complete graphs are labelled ki, where I is the number of vertices, and we can easily calculate the number of edges from the number of vertices. This was covered with the 8-bird flock in part 1.1. However, we need a firm black and white understanding of just what a null graph is, which is the graph with no edges and no vertices. Otherwise, it's not an empty graph. I'm definitely no Oyster Orr, and I don't doubt his logic. The key point I wish to get through here is that the terminology, if not standardized, can confuse readers, just as it did when I was trying to learn the subject. For this reason, I've used Dennis Koenig's and others' definitions of the empty or null graph to be just that, a graph containing no vertices or edges. Although Diestel is critical of the utility of null and trivial graphs, Jerry Seinfeld managed to get NBC to fund 9 seasons of a captivating television series about absolutely nothing. So there's always a place for nothing. We just need to know what nothing means in this instance. Incidence Function. Apologies, I thought I was absolutely crushing the animation, but I seem to have fallen short on the mark in capturing all of the actual elements in PowerPoint. So no surprises, we're going to be talking about functions and relations. The rule of association is essentially the recipe of a graph. It tells you what edges are associated with what vertices. The way in which we do this could either be an incidence relation or an incidence function. This is the key point of confliction or tension that I've found throughout most of the text. Do we use a relation because it can map a single independent variable to multiple dependent variables, thus not requiring inclusion of additional sets? Or do we use a function which can associate a unique dependent variable with each independent variable? I've opted for the latter and included the endpoint set, and I'll use a cupcake example in the next slide to show my thinking. Figure 20 shows our common simple graph G1, which has 3 edges and 3 vertices. The relation between the edge and vertex sets is shown. Note the bird's nest nature of relations. I've included EP 2011's definition of a relation and contrasted it with that of Balakrishnan in 1991. They're both essentially saying the same thing. The problem with a relation between the edge and vertex sets is that a single edge is associated with only one vertex in an ordered pair. So to associate an edge with a pair of endpoints, we would need to use something like the Cartesian product of the vertex set with itself, which would generate ordered pairs of vertices. This is only useful if we are concerned with directed graphs because the direction of travel is explicit in an ordered pair, for example a vector or a one-way road. The cake example. I've included this example at last minute to show my thinking on the relationship between the basic components of a graph, specifically whether or not to include the rule of association in its definition, or as it's more formally known, the incidence function. My logic is illustrated through the example of a cake, the recipe to make the cake and its ingredients. So, to make a cake you need ingredients. The types and quantity of ingredients influences the kind of cake that comes out at the end. Therefore, the cake seems to me to be the dependent variable in this relationship and the ingredients the independent variables. In this regard, we can think of an edge as the type of cake that is mapped to the endpoint set, which is the set of ingredients by the recipe, which is the incidence function. Walking around the slide, we'll explore the value of including or excluding the incidence function in the general definition of a graph. The cakes shown by C1 and C2 represent the graphs. Then moving below, the set of baked things or cakes is given by BC. The set of ingredients is given by TC, and the set of unique cake mixtures is given by MT. If we look at the way we map a specific cake to a number of ingredients, we get the bird's nest relation shown in the top middle, which is an absolute mess. If we, however, rethink the way that the sets are related and map the set of baked things to the set of unique cake mixtures, which have a mixed multi-set of ingredients, then it looks more like a function and less like a mess. The diagram in the bottom center shows the function, but it looks strange because the function is mapping the dependent variable to an independent variable. Instead, it should be swapped so that we're mapping an independent variable to a dependent variable. This is shown by the function of cake mixtures in the bottom right of the slide. As I said, apologies for the layout. This wasn't a planned addition, but I think it's valuable in showing that when people see a cake, they don't necessarily see its recipe. A lot of that is demonstrated in other disciplines as well. We see it with the atomic model. People don't see all the functions, the laws of thermodynamics. All they see are protons, neutrons, and electrons. In this regard, I think the same principle can be applied to graph theory, where we need to decide whether or not we include the incidence function as part of the graph definition. Incidence function. To wrap up this initial look at the incidence function, I've included an example I've come across in the consulted text and adapted it to our simple graph. The key thing I want to get across is that functions map independent variables in the domain to dependent variables in the codomain. So what's interesting in graphs is the question of whether the edges are independent or whether the endpoints are independent. Thus we enter into this cake and ingredient mix type scenario. But I do think the edges are independent because the image of this set of edge values is the set of endpoints in a graph. There may be some endpoint sets that are not mapped to by edges, but every edge is mapped to a unique endpoint set. Unlike the cake and ingredient mix scenario though, endpoints don't mean anything until they're mapped to edges. Ultimately, they're a pool of potential until they're given purpose by an edge. So, an incidence function is a relation that maps each element of the edge set, e.g., to an element of the endpoint set, SV. For every element EI that's an element of the edge set, there is a multi-set element VI, which is equivalent to SI, which is an element of the set SV, such that this ordered pair of the edge and the endpoint pair is an element of the function, or in this case the incidence function. And for all elements, which are edges, which are elements of the edge set, and the endpoint multi-set pairs, if we had two that were different, so VI, VJ, and another pair VI and VK, in the endpoint set, if the element EI, the edge EI, and the pair VI, VJ is an element of the function, and the pair EI and the pair of endpoints VI, VK is an element of the function, then VI, VJ is equal to VI, VK. So what on earth does that mean? Well, for one, it's confusing as hell when you speak it out loud like that, when you're trying to read the notation of functions. Essentially what we're saying is that for one unique element in the domain, which is EI, it can't map to two separate endpoint pairs. So VI, VJ is one endpoint pair, one endpoint multiset pair, and VI, VK is another one. So one edge can't be associated with two different endpoint pairs. So one edge can't map to two different edges, essentially. That's what we're saying. I think this is a very important property to get across at the start, because if we had multiple endpoint pairs that could map to separate edges, it wouldn't even be a relation. This whole relationship wouldn't make sense, so we wouldn't be able to develop a graph from that. So I do think that the edge set elements are indeed the independent variables, and the multi-set pairs of endpoint elements are the dependent pairs. Some sources define a graph as a 3-tuple or a triple, where G is equal to the triple of the vertex set, the edge set, and the incidence relation, where IR is the incidence relation. But I disagree with this due to the bird nest presentation of such a mapping. The incidence function is neither one-to-one or injective, nor onto or surjective, since the presence of isolated vertices and loops in a graph precludes the possibility of the function being either injective or surjective in the general definition of graphs. I have to say that looking back now, the example 1,2j is not the best to highlight why the incidence function is neither injective or surjective for general graphs, because the function in this example is actually injective. If we look at EP 2011, she states that an injective function is defined as follows. Let f be a function from a set x to a set y, where f is one-to-one or injective if and only if for all elements x1 and x2 in x, that is, two elements of the set X, x1 and x2, if the function of x1 equals the function of x2, so as you typically map from the diagram of two sets being two circles, if two elements in y or in the function of x that are mapped to by the function in the codomain, then x1 equals x2, because we can't have an element in a function in the domain that maps to two separate values in the codomain. There are some functions I'm aware of that this happens, but that's when you remove the y value from the left-hand side of the equation, square it and place it on the right-hand side, which isn't exactly street legal when we're looking at functions. So from a set builder notation perspective, the function that maps elements from set x to set y is 1-to-1 if for all values x1 and x2 that are elements of the set of x, if the function of x1 equals the function of x2, then x1 equals x2. And essentially this means any y value has at most a single x value that maps to it. This is shown in Rosen 2012's example of injective graphs in the slide as well. Defining a graph. To tie everything we've covered together into a single point, a summary of the defining graph features is shown below in Figure 21. Graphs consist of a vertex set, an edge set, and an incidence function that maps a single edge from the edge set to a corresponding pair of unordered vertices in an endpoint multiset, which is a two combination of elements of the vertex set with repetition of elements. These endpoint multisets are elements of the endpoint set S. Again, I seem to have failed to update the presentation. The incidence function is referenced as being 1-to-1 or injective above. However, they're generally not 1-to-1 or injective. There are some instances where they are, which was given in the previous figure. However, generally they're not. And the verbiage above doesn't neatly correspond to the diagram in Figure 21 below. Although most texts don't include reference to a set of endpoint multisets, this is what I believe to be inconsequential, as the endpoint set is essentially derived from the vertex set. I have, however, included it though, since the possible edges of a graph cannot exclusively be enumerated by sets and ordered pairs alone. Therefore, I don't believe this is an accurate depiction of a general form of a graph. Building blocks. Just as an interesting final perspective to the problem of what to include when defining a graph, I've included a brief look at the Bohr atomic model. Like the Bohr atomic model, where the basic building blocks or components of atoms are the subatomic particles being protons, neutrons, and electrons, in graphs, the basic building blocks are the vertices and edges, similar to the Bohr atomic model having the protons, neutrons, and electrons. And just like the atomic model, the concepts of valency, orbitals, and atomic mass are features. In the same vein, the concepts of endpoint sets and incidence relations are features in graphs. This is why most texts delimit the scope of graph definitions to its components, that is, an ordered pair of the vertex and edge sets, which is given by G equals VE, without including the endpoint set or incidence function as components. And just like the cake example, no one sees a recipe when they see a cake. But you can't make a cake without one, and you can't make a graph without an incidence function. Section summary. Well folks, that's it for part 1.2. In this presentation we covered the graph labeling standard using Balakrishnan and Ranganathan 2012 as the exemplar standard. We then formally covered off on the component terms, which were introduced in part 1.1 but were confirmed in part 1.2. We then introduced and covered off on the sets, being the vertex, the edge set, and the endpoint set. We also covered off on the order and size of a graph. On our journey to understand the null and trivial graphs, we then covered off briefly on walks, trails, and paths. Once we'd covered off on the walks, trails, and paths, we then covered off on the trivial graphs and the null graphs. We then looked at some general features of the incidence function and walked through the cake example. After that, we tied all of these features together in the graph components summary, which developed the standard definition of a graph and the 4 components, being the vertices, edges, endpoints, and the incidence function. A summary of the terms covered in this section are given below. This page is a summary of all the grey term tiles that were presented throughout this presentation. And that's a wrap for part 1.2, guys. Thanks for watching, and if this presentation was of value to you, please do like and share. Stay tuned for part 1.3, where we'll put the nail in the endpoint coffin and hopefully provide some clarity on why so much variation in endpoint terminology exists.